We are asked to find the derivative of this function right here, and this function happens to be an integral. So it sounds like a fundamental theorem of calculus part 1 problem. But this time, both our upper and our lower limits are functions of x. There are no constants in here. So we're going to have to mess around with this integral a little bit, and then I think by the end of the video, maybe we can come up with a general strategy for solving these types of problems. Okay, so technically to use the fundamental theorem of calculus, part 1, we need a lower limit of integration of a constant. Let's see if we can make that happen. Something that we're allowed to do is break an integral into 2 pieces. If we have an integral from x cubed to x to the 5th, we can instead integrate from x cubed to some constant, and then integrate from that constant up to x to the 5th. This area under this curve plus this area under this curve should add up to the area under this curve. So I think we can take the derivative of this integral here because we have a lower limit of integration of a constant. Here we have our integration constant switched, so we need to pull that trick again where we switch our limits of integration and we put a negative on our integral. And maybe it's just me being OCD, but I kind of want to switch these around. Now each one of these lines is just capital F of x. We want to find the derivative of that function. Fortunately, we can now use the fundamental theorem of calculus, part 1, to take a derivative of each of these integrals. Notice that we have a couple of composite functions here, so the chain rule applies. For the derivative of this first integral, we take x to the 5th and we plug it in for t here, and then we have to multiply by the derivative of x to the 5th. For the derivative of this second integral, we do the same thing except with x cubed. And let's see what we get. Okay, I just took the derivative of x to the 5th and x cubed, and there is really not that much we can do here with this function. Notice that this 2x to the 5th minus 1 is a different factor than 2x cubed minus 1, so we can't factor that out. We are able to factor an x squared out, and if you did that, it would look like this, and I think it's arguable which one of these two is the better answer. So I am actually just going to box this thing up and call this problem good. Now I'm going to zoom out a little bit here so we can see the beginning of the problem. And you'll recall that at the beginning of this problem, we split up the integral into 2 pieces so that we could use this fundamental theorem of calculus directly with a lower limit of integration of just a constant on both of these integrals. But what ultimately happened here? In this line here, it looks like all we did is we took this upper limit of integration, we plugged it in for t here, and then we multiplied by the derivative of that upper limit by the chain rule, and then we subtracted, and we plugged in the lower limit of integration, and we multiplied by the derivative of that lower limit of integration. And honestly, this problem is always going to work out so that you can do that each time. If I wanted to write out a general rule for this, you would have a derivative of the integral of a function, and both the upper and the lower limits of integration are functions of x. And you can see how ugly mathematical notation can get so fast. But the general rule is you take this upper limit of integration and you plug it into the function for t. Then you take a derivative of that upper limit of integration, you subtract, and then you do the same thing for the lower limit of integration. You could call this a corollary of the fundamental theorem of calculus if you'd like. But if you'd like, that is a general strategy that you can use to do these problems. All right, let's call this thing done. Thanks for watching and good job.